Hello, in this video we'll zero in on poison pills that occur during deserialization. A poison pill typically refers to any message the consumer can't handle. That might be due to application logic errors, validation failures, or deserialization problems. But in this scenario we're focusing on truly bad bytes, messages the Avro deserializer can't parse, like when someone writes a JSON payload to a topic instead of Avro bytes. Let's first see what happens right now when our consumer encounters a serialization error. We'll comment out our runner, we don't need to write any other events for now. Then, we'll make sure our consumer listens to the user activity topic. We can now go into Control Center under the Messages tab and we'll produce a new message here without using a schema. We get a warning that this might cause issues with downstream applications, which is exactly what we want. And now we can enter pretty much anything for the payload. This will be sent in a UTF-8 encoding, definitely not the user activity Avro that our consumer is expecting. So let's push it to our topic and fire up the consumer. Looking at the logs, we can see that it gets stuck in a loop, repeating the same issue. A deserialization error occurs when the application tries to consume the message we published. Our consumer can tell straight away that this message is not Avro encoded, as it's missing the magic byte. Spring Kafka consumers work by invoking a poll method, which fetches the next bytes from the topic and tries to deserialize them. If the poll call fails, the message will not be acknowledged and the consumer will just reinvoke poll indefinitely. To solve this problem, the error handling deserializer has been introduced. Let's configure it in application.yaml. This deserializer acts as a wrapper around the class that will actually perform the deserialization, and we specify that through the consumer properties. We rerun the application and now the error is only logged once and the message is acknowledged. It's important to also note that the consumer record was not passed to the listener. This is great because our consumer is now more resilient. It can handle deserialization errors without getting stuck. Spring also enables us to customize how we handle deserialization errors. To achieve that, we can create a function that receives an object of type failed deserialization info, which contains some context around what went wrong and returns an object of the type that we should have upon successful deserialization, in our case, user activity event. In this function, we'll log the bytes that we received from Kafka and their UTF-8 decoding. If we return null, Spring will know that something went wrong, will consider the consumer record corrupt, and will not pass it to our listener. To have Spring use this function, we'll leverage once again the app properties, and under Spring deserializer value function, we'll specify its name. I will rerun the application and publish another invalid message. Our consumer invokes our function, it then logs the deserialization error and moves on. If, however, we return an actual object instead of a null reference, Spring will actually pass this event to our listener. So let's build a user activity event here, rerun the application and publish another message. We get our log from the function, but also the logs from within the listener. And there's no longer any deserialization exception here, because it's no longer treated that way. Alright, let's revert to returning null references here. We now have a pretty resilient consumer that can also provide some custom information around deserialization problems, all with just a few lines of code. That's the true power of Spring Kafka. Moving on, it's time to write some tests. We want test cases that are very close to what happens when we run the application, so we'll need some sort of integration test setup that allows us to talk to Kafka and the Schema registry. Functionally, we want to have easily repeatable proof that our consumer is able to handle both the happy path when it receives Avro encoded messages, but also the scenario when it receives a poison pill. A great tool for that is test containers, which will allow us to easily configure and spin up containers for our tests. Let's first add the required Maven modules, test containers, which provides programmatic Docker access from our Java test classes. Spring Boot test containers, which helps us with the integration between Spring Boot and test containers, JUnit Jupyter from test containers. This will give us some useful annotations and lifecycle hooks to manage containers within JUnit 5 tests, and Kafka from test containers, which should cut some of the boilerplate required to spin up a Kafka container. We can now prepare our codebase for testing. We'll extract our listener logic in its own Spring component in the shape of a Java consumer function. This will allow us to easily mock the Kafka listener when we need it. Then we can start writing the setup for our tests. We create a network similar to how you might create one in a Docker Compose environment. It will be shared by our Kafka and Schema registry containers. We'll set our containers version to 780. To define a Kafka container, we simply instantiate a Confluent Kafka container. We'll add two annotations to it. Container, which will enable test containers to manage its lifecycle for us. It will automatically spin it up when the test class starts and will shut it down when it finishes. Then we'll use service connection, which automatically registers the Kafka broker's connection details in Spring Boot's application context, making the Bootstrap server's address available to our Spring Kafka producers and consumers without manual configuration of connection properties. Pass it the Docker image name and tag. We'll set its network as the one we created above. We can also provide it with an in-network alias of test containers Kafka, and finally we set up a listener within that network for port 19092. We can now move on to the Schema registry container using again the same lifecycle annotation. We don't have a specialized class for it, so we'll just use a generic container, pass the Docker image name and tag, add it to our network, configure its listener, let it know where and how to reach Kafka, and finally perform a startup health check by waiting for a successful response from its subject endpoint within a minute. We also need to let our in-test consumers and producers know where to reach this Schema registry instance, which is why we have to add a dynamic property source. Finally, to really try to get as close to reality as possible, we'll want an environment where we not only have Kafka and the Schema registry up and running, but also where the user activity event schema is already registered when we start producing and consuming messages. If you remember, that's how we did it when we first started playing with Avro-powered producers. So let's create a before all hook, where we once again get the registry URL, and with it, we create a Schema registry client that we can then use to register our user activity event schema to our user activity value subject. Now that is a complete integration test setup and also a pretty good overview of many concepts that we've seen in this course so far. Let's write our first test for the happy path. We want to verify that Avro-encoded events make their way into the Kafka listener, which is why we'll use a mock bin for our consumer handler. We'll create a sample event and send it to our topic, and then we'll verify that it has indeed reached our consumer handler. Start the test, which by the way may take a while on its first execution because it will have to fetch the Docker images. After it's done, we can see that everything went through. We can also write a test for deserialization poison pills. Let's test this one by producing a poison pill, then producing a valid user activity event and checking that the valid event reaches our consumer handler. This way we know that the consumer was able to go past the poison pill. To produce a poison pill, we can write a string message instead of an Avro one. For that, we can't just use the Kafka template that we usually inject, because that one is configured to use the Kafka Avro serializer, and it won't accept receiving a random string as its input. So let's create another producer that expects string type inputs. We'll define it in a test configuration class called Kafka test configuration. We'll use a functional interface with a send method and register a bean that implements this interface. We can just copy our usual producer configuration, replace the serializer, instantiate a new Kafka template, and use its send method to implement the string producer interface. Going back to our test class, we can import this configuration, which will give us access to our Spring Producer bean that we can then inject and use in our test to write a poison pill. Then it's time to write our valid message and assert that it reaches our listener. Let's run the entire test class. We got a green light for both tests. That concludes the end of this video. I will push this code to our GitHub repository under a commit called poison pills and test containers. Since we unpacked a lot of information in this video, I highly recommend that you take your time and play a bit with this codebase. Maybe write some more tests, try to tweak the test containers config and see what happens, or explore the functionalities provided by the Schema registry client that we used in our test suite. And thank you for watching. I will see you in the next one.